In this pencast, we will see how to calculate the autocorrelation function and the power spectral density. To learn how to do so, we will take this exercise as an example. In this exercise, we have a random process X generated by filtering innovation I, which is a white noise sequence with zero mean and unit variance, with a filter with the system function given in the slide. From the system function, we can observe that this system has a 1, 0 and 1 pole. So it's an ARMA process, an autoregressive moving average process. And in this exercise, we are asked to calculate the autocorrelation function and also the power spectral density in two different ways. There are different ways to calculate the autocorrelation function. In this pencast, we will focus on the method based on the difference equation. Alternatively, we could also use the modified U-Walker equations. First of all, let's remind what is this system. So we said that the process X is obtained by filtering innovation with the system function given here. So to obtain the difference equation, the first thing we need to do is to obtain the inverse of the system function. Let's first remind that when we have a system defined by the system function hz, in the z domain we can calculate the z transform of the output, y of z, as the product of the z transform of the input, h of z, multiplied by the system function, h of z. And therefore, in this case, where the input is I and the output is x, I can rewrite this like that. And this also leads to this equation. Now, what I need to do is to expand these products to obtain this equation. And then, from this equation, calculating the z transform is easy by using the time shifting property of the z transform. This property tells me that if I have a signal x and I shift the signal of a quantity n0, then in the z domain this is equivalent to multiplying the z transform of x by z to the power of minus n0. By this property, iz is simply I of k, and xz the same, x of k, while this one becomes minus 1 over 3 I k minus this shift, so minus 1, and the same for x. So applying the time shifting property, I easily obtained in the time domain the transform of this equation in the z domain, and the last step is to rearrange to have x of k on the left side of the equation to obtain finally the difference equation. Now, before we proceed with the calculation, we can first stop and think a bit about which kind of structure we expect for the autocorrelation function of x. Remember that we said that this is an ARMA process, so the signal is generated by an ARMA process, and we saw that the signal has 1 pole and 1 zero, so can be seen as an ARMA process of order 1 and 1. When we look at the modified U-Walker equation, we know that until lags equal to the number of zeros, that in this case is 1, we have both the contribution of the moving average component and the contribution of the autoregressive component. While for lags larger than 1, larger than the number of zeros, only the autoregressive components plays a role. What does this mean in practice? In practice, it means that for lags larger than the number of zeros, I only have the autoregressive components, and therefore I can find a recursive structure in the autocorrelation function. While for lags that goes from 0 to the number of zeros, I have both the moving average and autoregressive components, and therefore I cannot find a recursive structure, and I need to calculate the autocorrelation function for each lag. So with this in mind, we can start first by looking at the lags smaller or equal the number of zeros, and then look at the recursive structure for lags larger than the number of zeros. So we have here the difference equation, we have here the definition of autocorrelation function. So we need to calculate this for lags 0 and plus minus 1. At 0, we obtain that tau is equal to 0, and therefore we are left with the expectation of x squared. And here we simply substitute for x squared the difference equation. The next step is to expand this square, and given the linear property of the expectation operator, separate each component of the square. Now let's look separately at each of these components. This one is equal to multiplying ik times ik. So it's like the autocorrelation function of I for lag equal to 0. And this one is the same because it's like multiplying ik minus 1 times I at k minus 1, which is again the lag is equal to 0, and therefore is the expectation of this is equal to the autocorrelation of I at 0. But let's remember what is the autocorrelation of a white noise sequence. This function is given by a delta pulse in 0, whose amplitude is given by the standard deviation of the input noise. Therefore, these two, they both give me a contribution of sigma I squared. For the same reasoning, this is equal to the autocorrelation function of x, this time at lag 0. And now we need to look more carefully at this one, and this one. Now, for the first one, the expectation of ik times ik minus 1 is equal to 0, and this is because, again, the autocorrelation function of I is a delta pulse in 0, while it's equal to 0 for any lag larger than 0, because the noise samples are uncorrelated. You can see here that the lag is equal to 1, and therefore this expectation is equal to 0. The second one is the product of ik times xk minus 1, and this is also equal to 0. And to understand why, let's expand x. So you see here we expand x by substituting for the difference equation. And now what we can see is that the first term here is actually the autocorrelation of I for lag 1, and we already saw this is equal to 0. The second term is the autocorrelation of I for lags 2, and this is also equal to 0. And finally we have this one that gives me the expectation of ik times xk minus 2. We can expand again xk minus 2 by looking at the difference equation. So we need to shift the difference equation by 2. And from doing this, we obtain ik minus 2 minus 1/3 ik minus 3 plus 1/2 xk minus 3. And if we expand this again, we obtain ik minus 3 minus 1/3 ik minus 4, and so on. So from this we can observe that x shifted by 2 will give me noise components, so innovation sequence components, that are shifted of at least 2 lags. So from this product, I will have several different products, but always of ik times ik minus L, where L is always larger than 0. And therefore, this product always, the expectation of this product always gives me a 0. So this was 0, this was 0, and also ik times this gives me 0. Well, after calculating 1 and 2, number 3 is actually trivial because we have the same components as before. When we expand x of k minus 1, we obtain this in parentheses, and then here we obtain the autocorrelation of I for lag equals 0, and this gives me sigma I squared. But then the rest, here again I have the autocorrelation of I for lag equal to 1, and this one is exactly as the case before. I get expectation of I k minus 1 times x k minus 2, and this will give me noise components for shifted of L with L always larger than 1, and therefore the expectation of this product will give me 0. So the only component different than 0 is the first one, and I get sigma I squared. Now we just need to put all the pieces together, and we get at the end that the correlation of x at lag 0 is equal to 28 over 27. Now, with very similar reasoning, we can also calculate the autocorrelation of x at lag 1, and we obtain in this case that the autocorrelation at lag 1 is equal to 5 over 27. Here again we have the same components as before. Ik times x k minus 1 is equal to 0. This one gives me a sigma I squared component, and this one is the autocorrelation of x for lag 0. And remember that sigma I squared is actually equal to 1, and that's the reason why here I simply write 1 over 3. Now we are at step 3. We have calculated already the autocorrelation function for lags smaller or equal the number of zeros. And we have found that in 0 the autocorrelation is 28 over 27, and in 1 and equivalently in minus 1 is equal to 5 over 27. The next step is to calculate the autocorrelation function for lags larger than the number of q, for which only the autoregressive components plays a role, and therefore we will be able to find a recursive structure and express the autocorrelation function with a formula. While these two are similar as before, this is equal to 0, this is also equal to 0, and the only component I've left is this 1/2, the autocorrelation at 1. Similarly, we can obtain the same for the correlation lag 3. We have two components equal to 0, and this one, this time, is the autocorrelation of x at lag equal to 2. But this one we know is equal to 1 over 2, the autocorrelation of x at 1. So now we can already appreciate the recursive structure given by the autoregressive component. If we calculate the autocorrelation at 4, we obtain something similar. We will obtain 1/2 times autocorrelation at 3, which is equal to 1/2 autocorrelation at 2, which is equal to 1/2 autocorrelation at 1. And we can go on the same for 5, 6, 7. And when we see this recursive structure, we can easily calculate the autocorrelation function for lags larger than 1, as given by the product of the autocorrelation at 1 for 1/2 to the power of the absolute value of tau minus 1. While for the lags equal to 0 and plus minus 1, we are dependent on the moving average component, and therefore we need to express the autocorrelation function separately. So this is the final formula for my autocorrelation function. Apologies that I used basically interchangeably tau and L, but I hope you don't get confused. Tau and L are both basically the lag. And what we can observe is that if we plot the autocorrelation function, we obtain the largest value at 0, and then for minus 1 and 1, we have both the contribution of the autoregressive component and the moving average component, while for a lag larger than 1, we only observe the exponential decay given by the autoregressive component. Once we have calculated our autocorrelation function, we are asked to calculate the power spectral density of X in two different ways. Well, the first way, that in this case is more straightforward, is using the input-output relationship of an LTI system. We know that when we input an LTI system with a random input, we obtain a random output, and because of the relationship between the output and the input given by the system function, we know that the power spectral density at the output is given by the power spectral density at the input multiplied by the modulo squared of the frequency response of the system. To calculate the frequency response of the system given the system function, we simply need to evaluate the complex variable z on the unit circle. And if we do so, we obtain this expression where we have substituted for the power spectral density of the input noise, the standard deviation of the variance of the input noise, which is equal to 1. And for the frequency response, the system function evaluated on the unit circle. Now, to simplify this part, we just need to remember that e to the power of j theta is equal to cosine theta plus j sine theta, and also that sine of minus theta is equal to minus sine of theta, while cosine of minus theta is equal to cosine theta. So by making these substitutions, we obtain the expression here in the slide, and then we can substitute for the modulus squared the square root of the real part squared plus the imaginary part squared on both numerator and denominator. And then rearranging the terms, we can remove the square with the square root, and we can expand the square. And to further simplify this, we can make use of the fact that sine squared theta plus cosine squared theta is equal to 1. And by using this fact, we can finally obtain the power spectral density of X as given here in the slide. A second way to calculate the power spectral density when we know the autocorrelation function is to use Wiener-Khinchin theorem that tells us that the power spectral density of X is simply calculated by taking the Fourier transform of the autocorrelation function. And before we do this, we can also observe, here we define the autocorrelation function for each lag, but we can see that when we apply this formula for lag equal to 1, we obtain exactly 5/27. So this formula is also valid for tau equal or larger than 1. With this in mind, we can substitute for the autocorrelation function the autocorrelation function is 0, and then for tau that goes from minus infinity to minus 1, we have this expression, but also for tau that goes from 1 to plus infinity. Well, now we can look at this sum, and we can actually switch it from a positive sum by changing the sum from tau equal to 1 to plus infinity, but then since we change the sign, we need also to change the sign of tau. So here it becomes minus tau, and here it becomes minus tau, and thus plus tau. But now, since these sums are both positive, we can also remove the absolute value, because tau is always positive in both sums. To express these sums in a closed form, I can make use of this infinite series that says that when I sum from 0 to infinity x to the power of n, I get 1 over 1 minus x, valid for absolute value of x smaller than 1. However, these sums are not from 0 to infinity, they're actually from 1 to infinity. So I need to find a way to express this in a form that is more similar to this infinite sum. But if I change this sum from 0, so suppose I have another summation variable that is equal to tau minus 1, then for tau equal 1, like here, this summation variable is equal to 0. So I can substitute it here. But then I also have to change for tau alpha plus 1, because this is a new summation variable. And if I do this in both sums, it should be easy to see that this summation, when I change the limit of summation to 0, becomes this sum. And now this complex exponential can also be rewritten as e to the power of j tau theta times e to the power of j theta. And because this doesn't depend on tau, I can also take it out of the summation. And if I do this for both sums, I obtain this expression. And now this part is really similar to that infinite sum I showed before, because this can be rewritten as 1 over 2 e to the power of j theta all to the power of tau. And this one is always smaller than 1, because the complex exponential has a radius of 1, and 1 over 2 is clearly smaller than 1. And similarly, this sum becomes 1 over 2 e to the power of minus j theta all to the power of theta. So remembering once again the infinite sum, from the first sum I get 1 over 1 minus 1 over 2 e to the power of j theta. And from this one I get 1 over 1 minus 1 over 2 e to the power of minus j theta, which leads to this expression. And then it's a matter of rearranging these terms, so I can rewrite this by taking the common denominator, and from this I obtain 1 minus 1 over 2 e to the power of minus j theta minus 1 over 2 e to the power of j theta plus 1 over 4, and at the numerator I get e to the power of j theta minus 1 over 2 plus e to the power of minus j theta minus 1 over 2. And remembering Euler's formula that e to the power of j theta plus e to the power of minus j theta over 2 is equal to cosine theta, I know that this gives me cosine theta, and here I get 2 cosine theta. So this can be rewritten like this, and on the denominator I have 1 plus 1/4 minus cosine theta, and at the numerator I have minus 1 plus 2 cosine theta, and this is equal, of course, to 5/4. And finally, by substituting for r of 1, 5/27, and r of 0, 28/27, and making the calculation, I obtain the same expression as with the first method, that was via the input-output relationship of an LTI system. To wrap up, we were asked to calculate the autocorrelation function and the power spectral density for a signal X that was obtained by filtering innovation by a system defined by this system function. And we calculated the autocorrelation function, given here by this formula and represented here by this plot. And we also calculated the power spectral density with two different methods, namely by the input-output relationship of this system, and also by using the Wiener-Khinchin theorem. And we obtained this expression for the power spectral density. And when we plot the power spectral density, we can also observe that, as expected, this function is symmetric and is also positive. This concludes this pencast on the calculation of the autocorrelation function and power spectral density for an ARMA process. Thank you for listening.